Okay, so we're going to first solve questions from the vector analysis chapter. And these are some questions that you sent me. And we're going to solve this question first. Okay, so our first question is about finding the velocity of a rotating vector. So first, let's write down what we have here. We're given three vectors. Vector A, which is 1, 1, minus 2. Vector B, which is 2, minus 1, and 3. And vector C, which is 0, 1, and minus 5. Now, in the question we are asked, A and C are drawn from a common origin, and C is rotating about A. So the picture you have to have in mind is as follows. You have vector A and vector C, like this, from a common origin. And C is rotating about A with the velocity of 2 radians. So C is rotating something like this, about A. So this means that the angular velocity is along A. Since it's rotating about A, that makes sense. Now we're given that omega is 2 radians per second. But A might not be 2 units of 2. So you have to make A to have 2 units. So let's first find the length of A, which, if you remember, is given by the dot product, i.e., the length of A is the square root of the dot product of A with itself. So what's the dot product again? That is 1, 1, minus 2, dotted with itself. The dot product is simply the product of individual components and the sum. So I have 1 times 1 plus 1 times 1 plus minus 2 times minus 2. So this is simply 2 plus 2 plus 2, which is 6. Now I need to take the square root of this if I want the length itself. So what will I have? Square root of 6 units. This is the length of A, but we're given that omega is in fact 2 radians per second. So you have to multiply and divide by 2. So I'll have, first I have to divide by square root of 6. In that case, I'll have a unit vector, and I have to multiply by 2. So in this case, I'll get omega, because omega has 2 unit lengths, and it's parallel to A. This is the vector we need, omega. Now, to find the velocity, we have this equation, V equals omega cross R. Now, to justify this, you may look at it like this. I have, say, a vector that is rotating with an angular velocity omega. So the picture should be something like this. And suppose it's rotating counterclockwise, so it's like this. You can see that the tangential velocity at any given point goes something like this, perpendicular to the radius of rotation. So this is velocity, this is omega, and this is R. If you look at the interpretation of the cross product that we've seen in class, if I take the cross product with omega cross R and I use the right-hand rule, I see that it's pointing in the right direction, in the direction of V. So you can justify it like that. But there is actually a more rigorous way of doing this, but we'll not go into that. We'll just take this as it is. Now, we also have to find R. In this figure, what do you think R is? Anyone wants to have a guess? No guesses? Okay, I'll just okay, so someone will record it. There's no issue with that. This is just respond to the chat. Okay, so R is basically this, the vector C, since C is the one that is rotating like this. So now I need to do the cross product here, omega cross R. Omega we found was 2 over root 6a crossed with C. C is R. So I'll have I, J, K. This is by the definition of the cross product. I'll have 2 over root 6 outside because if I have something vector multiplied by scalar, I can take it out in the cross product. So what is A again? A is 1, 1, minus 2. 1, 1, minus 2. And C is 0, 1, minus 5. I'll just quickly compute this cross product. So I'll have minus 5 plus 2, which is, don't forget the 2 over root 6, minus 3, and the jth component is minus 5, 0, plus I have the minus sign in here because, there's this factor of plus, minus, plus in here because of the determinant. So I'll have this plus, and the kth component which is 1 minus 0, which is 1. So this is my velocity in meters per second because they gave you the units of omega. They gave it to you in radians per second, so this must be in meters per second. Okay, so this is the answer to the 5th question. Now the next one, it tells you, the question tells you, draw B with its tail at the head of A. If the figure is rotating, as in problem 5, as in it's rotating at 2 radians per second, with the same, find the velocity of the head of B. So what we did for C, we have to do it for B now. But in this case, it's not the vector B itself, but it's starting from A. We're talking about this vector. With its tail at the head of A. So if this is A, this is the vector they're talking about, the vector AB, if you will. Okay, so it's rotating as in problem 5. Find the velocity of the head of B. With the same diagram, let B be a force. Find the torque of B about the head of C and about the line C. Okay, this is the second part. We'll do it later. First, we'll just do this one. Okay, so this is the 6th question. I have vector A and I have vector B, which had the same origin before, but now A is the origin here. All vectors start from A. Since the question tells you that the tail is at the head of A, that means that A is the origin. You can no longer consider 0, 0, 0 to be the origin. Okay, so this is rotating like this, right? So I have, again, A is angular velocity. They're telling you that it's rotating in the same direction, so omega is not changed. Omega we found in the last question, 2 over root 6a. So we'll have, again, V equals omega cross R. But now R is AB, the vector AB. And if we look at quickly what A is 1, 1, minus 2, B is 2, minus 1, 3, A is 1, 1, minus 2, and B is 2, minus 1, 3. Okay, so I have AB, the vector AB is B minus A. This is the definition of the vector starting at A and ending at B is B minus A. So I'll have 2 minus 1 is 1, minus 1 minus 1 is minus 2, and 3 minus minus 2 is 5. So this is AB. This is my R. Now, the velocity is simply ijk, the cross product with omega cross R. So omega is, as we said, 2 over root 6, 1, 1, minus 2. And R is 1, minus 2, 5. I'll compute this again quickly. So I'll have 2 over root 6. And I'll have the ith component is 5, minus 4, which is 1. And the jth component is 5, plus 2, which is 7. But I have a minus sign here from the determinant coefficients. So I'll have minus 7. And again, I have the kth component, which is minus 2, minus 1, which is minus 3. This is our velocity, and this is in meters per second. Okay, so let's look at the second part of the question, which is this one. Let B be a force. Find the torque of B about the head of C and about the line C. So in this picture, what would that be? Let's draw it. I have a vector C here. But remember, A is our origin now. We can no longer consider this to be our origin because A is our origin now. So if you want to find R would be from here, from A to C, like this, the vector AC. Okay, so, and they're giving us that B is the force. So B equals F. We're asked to find the torque of B about C and about the line C. So we have done something similar in class. So to find torque, we need R cross F. This is the definition of torque. And R is the vector AC, as we argued, which is C minus A. And that is, let me just look at what C is. C is 0, 1, minus 5. And A was 1, 1, minus 2. If I do this quickly, I have minus 1, 0, minus 5 plus 2, which is minus 3. This is our R. Now F they gave us is simply B. And B was 2, minus 1, and 3. And yes, so the torque is IJK, the cross product of R cross F. Again, remember, torque really depends on the order of the vectors. And if I take F cross R, that will give the negative of torque, not torque itself. This is something that you should keep in mind. So let's just write down R and F. R and F. R is minus 1, 0, minus 3. And F is 2, minus 1, 3. If I do this quickly, I'll get 0, minus 3. And the jth component is minus 3, plus 6, which is minus 3, but I have minus 3 plus 6, which is plus 3, but I have a minus sign here, so I'll have minus 3. And the kth component is 1, minus 0, which is 1. And this is in Newton meters. This is torque of B about C. Now they're asking us find the torque and about the line C. If you have a question like this, they're asking you, this is tau, and I have C like this. They're asking me the component of tau on C. Now, if I have to find something like this, what I have to do is take the dot product with the unit vector of C. So this will give me a scalar, because the dot product gives me a scalar. Now, what is the unit vector of C? So for this, we need to find what C is first. C is 0, 1, and minus 5. So finding unit vector of C is vector C over the length of C, which is 0, 1, minus 5. And you can check that this is 1 plus 25, which is 26, square root of 26. And so I'll have tau, we found this here, this is tau. And this is minus 3, 1, dotted with 0, 1, minus 5 over square root of 26. And now I should remark that, for the dot product, the order doesn't matter. You can take C dot tau and it will give you the same answer. Now, if I compute this quickly, I'll get 0, minus 3, minus 5 over square root of 26, which is minus 8 over square root of 26 units. The units would be Newton meter. Okay, so we've finished this question completely. We finished this and this. Now let's move on to the next question, which is this. Okay, so this is a very general question. They're not giving you, they're giving you a vector v of t, but they're not giving you what it is actually. And they're asking you to compute this integral. So this is I, let's say. And yeah, so we have to deal with this. How do we start here? So I have to integrate v cross d squared v over dt squared dt. Now, let's denote this by v double dot, the second derivative of v with respect to time. Now, how do I go about this? Let's see what we do when we have a function that is not a vector. Let's say we have f g dt, where f and g are functions of t. What will you do? What you will do is you'll take integration by parts. So I have f times integral of g dt minus integral of df over dt times integral of g dt. This is from your calculus courses. You should be familiar with this. My claim is that we can actually use this same integration by parts over here. We can take cross product and we can treat it just like a regular multiplication. And it works out. I mean, you can check this. There are probably proofs of this using tensors, but we don't need to go into that. We'll just use this as it is. So if I do integration by parts here, I'll have v crossed with integral of d squared v by dt squared dt plus integral of, so I have df by dt, so this should be dv by dt times integral of d squared v by dt squared dt. This whole thing, the integral of the whole thing, as we saw here. And okay, let's do this. So we know that integral of v double dot dt just removes one of the dots. right? Since, fundamental theorem of calculus tells us integral of d by dt of some vector v or some vector a is going to give us a itself plus some constant. Same thing here. We have a constant here. So this is this part of the integral. So I'll have v cross dv by dt. This is what we got here plus c. Okay, so and now let's do the second part of the integral, which is this one right here. So I have integral of dv by dt, and by the same fundamental theorem of calculus for vectors, I can just write d squared v by dt squared dt as dv by dt up to some constant. Let's ignore this constant, because we can take the constant to be 0. Okay, so I'll have dv by dt crossed with dv by dt. We have this thing. Now, how do we compute this now? If you remember, one of the properties of cross product was the cross product of a vector a with itself is 0. This was by the definition of the cross product. If you have ijk, you have the components of a in here, and again the components of a in here. And one of the properties of the determinant is that if you have two rows or two columns similar to each other, if they're the multiples of each other, then the determinant is 0. Okay, so using this, we can say that this is 0. So this whole thing goes to 0. So at the end, we'll have the result of the integration is v cross dv by dt plus some constant. We can take the constant to be 0, but let's keep it as it is. Now, can we do anything further with this? Can we simplify this any further? Do we have any relation between v cross dv by dt? Well, let's look into it. So I have v cross v is 0. Now, if I take the derivative with respect to time on both sides, like this, what will I get? I'll get, using the product rule, I'll have dv by dt crossed with v plus v cross dv by dt equals 0, because this thing is 0. Now, if you remember, another of the properties of the cross product was that a cross b equals minus b cross a. If I take this to be b, this to be a, this is equal to negative of this. So yeah, in that case, it makes sense. This would cancel out and you'll get 0. But does this actually tell us that v cross dv by dt is 0? Not really. V cross dv by dt can be anything. All it matters is that this is the negative of this, and you'll get a 0. So we cannot really do anything else with this. So this is our final answer. Okay, so we've solved this problem. Let's move on to the next one, which is this. We're asked to find the curl of a vector field. Now, let me give you a reminder. We've actually solved this problem exactly in our last lecture. And then I've used the del operator in spherical coordinates, which went something like this. Suppose I have F, a vector field. I have H1, E1. E1 is the basis in spherical coordinates. H2, E2, H3, E3. And H, if you remember, were the scale factors. And the scale factors were derived from the arc length element, the ds, which was dxi plus dyj plus dzk for Cartesian coordinates, for spherical coordinates, you had dr, er hat, plus r d theta, e theta hat, plus r sine theta, e phi hat. And for cylindrical coordinates, these two are repeated. These two are repeated. And you only had an extra dz in here. So dz ez hat. So the scale factors you could remember were these things. One in here, one in here. These were the scale factors. Okay, so basically you had partial x1, partial x2, partial x3, and I had again h1, f1. F1 is the component of f, of this f, f1, f2, f3, h2, f2, and h3, f3. This is a reminder of the curl in an orthogonal coordinate system. Again, a reminder, this formula works only when we have a basis that is orthonormal, like I, j, k. The angle between each basis is 90 degrees. If you have a basis like this will not work. This formula will not work. Again, this is a reminder, and I've already solved this in that lecture that I mentioned. So today I'm going to solve it in a different way. I'm going to solve it using Cartesian coordinates. So first, they're giving me r is x, y, z. So r over the length of r is x, y, z divided by square root of x squared plus y squared plus z squared. Now for Cartesian coordinates, h1, the scale factors are all 1. So h1 equals h2 equals h3 equals 1. So the curl of r over the length of r, let's call this squiggly r. Again, this is a notation that comes from Griffith, who is the author of the book for electromagnetism, which you'll take next semester. The course is usually offered in the next semester. Okay. So yeah, let's write down the definition of the curl. Partial x, partial y, partial z. And again, a reminder, partial x means partial x. This is a shorthand. Okay, so I have the x component, as you can see, is, for convenience, let me just call this r without a vector. So x over r, y over r, and z over r. Now let's compute this curl. So remember, r has x, y, and z in it. So you cannot just say that this is 0 by default, because r has all of the variables inside it. So you cannot ignore this derivative. So let's see, partial y of z over square root of x squared plus y squared plus z squared. You can treat z as a constant, and you can just say that this is some constant over some other constant plus y squared. So I'm just focusing on the variable of the derivative itself. So how would you usually integrate? I mean, take the derivative. If this was a one variable function, you'd just take nx raised to n minus 1 times x prime. If you have, since this is a what do they say? This is a composite function. U equals some function of x. So if you take the derivative here, if you take du over dx, composite function means it is not a variable of x itself. Theta is a variable of x. So I have du over dx is du over d theta over dx. This is again the chain rule. So if I apply this here, what will I get? I'll have, this is some function, square root. So I have minus 1/2, and If I take this to be r, I'll have r raised to minus half minus 1 times dr by dx. I mean partial r partial y using the chain rule. So I have partial y of z over r is simply z times r raised to 3 halves, which comes from the derivative of this, and the partial r with respect to y, which is remember r is x squared plus y squared plus z squared. So partial r partial y. I should have called this something different because r is defined as square root of this. So let's take this r tilde. So it's different. Partial r partial y is simply 2y. So I'll have 2zy over r raised to 3 halves. R tilde raised to 3 halves, actually. So you know what? I can just write it like this with respect to this r itself. So I'll have r raised to 3 in that case. And similarly, if I do this, I'll have partial z of y over r. You can check this. This is simply 2yz over r raised to 3. But remember, you have a minus sign when you do this multiplication. The off-diagonal multiplication has a minus sign. So if I take the ith component, I'll have this minus this. So 2zy over r cubed minus 2yz over r cubed, which is 0. This is the ith component. That's what we did right here. Now, if you proceed with the calculation, it's a similar computation, really. Each time you'll get something expression like this. I'll have 2xy minus 2xy, which will give me 0. And I'll have 2yz minus 2yz, which will again give me 0. These are the kth component and the jth component. You can check this. So at the end, I'll have r over r hat. I mean, the length of r will give me 0. This is the answer. You can also do it similarly for this and this. I've done them in the last lecture. If you want, you can have a look over that. And we'll move on to the next question here. Okay. This is again a question that a similar question had been solved in the last lecture, but I'm going to do it again for review. So yes, this is again to do with conservative fields. A field F is conservative. This is a reminder for you. If line integral of a closed path is 0. So suppose I have a path that starts and stops at the same point and goes like this. And if the line integral of this path is 0, and this is true for any given path, not just this. I can start like this, path like this. I can have a path like this, or something like this. For any, you can take any closed path, and if the line integral is 0 for all those closed paths, then f is said to be conservative. Let me just write this is conditions for conservativeness. So this is one thing, and another thing is if f dot dr, where dr is dx, dy, dz, is an exact differential of some scalar function. So this, if you remember, if phi is phi of xyz, from the chain rule, you had partial x phi I hat plus partial y phi j hat plus partial z phi k hat. If you can express f dot dr as an exact differential, then f is again conservative. Okay, so the third condition comes from Stokes' theorem. And this basically tells you that if curl of f is 0, then you're guaranteed to find a function phi such that the gradient of phi gives you f. Again, remember, the gradient only acts on a scalar function. The gradient usually doesn't act on a vector. I mean, there are quantities like this, but the meaning of those requires that you know tensors. You'll get a tensor quantity, and we don't really study that here. Well, anyway, these are the three conditions to know if f is conservative. In this case, you're given f on its own. You're not given any paths, any closed paths, or and you don't have a line integral, so you can check that it's an exact differential. So in this case, you'll have to use this condition, the Stokes theorem condition, where you just take the curl of f and see if it's 0. Again, in the test, if you're given a vector field and you're given a line integral like this, suppose I have 2xy dx plus minus x squared plus y squared dy, you can check like immediately if this is a closed path, and you're asked to find the value of the line integral. You can check if curl of f is 0, and you can immediately say that this line integral will be 0 without even doing any computation. This is a double check. Like of course you do the integral itself by setting up the limits and everything, but you can double check if your answer is correct by checking if your curl is 0. This is in cases where you have a closed loop. Again, in the last lecture, I've showed you like how you can use Stokes' theorem to simplify line integrals. You can check that out if you want more exercises. So the vector field here is 1 minus z minus y. Let's do this quickly. Partial y of minus y is minus 1, and partial z of minus z is minus 1, but I have a minus sign, so I get a plus 1. This is the ith component. Now minus j, this will give me 0 because partial x of y is 0. This will also give me 0. So yeah, and the kth component is, this is 0. This is also 0. So at the end we'll get a 0. So we can conclude that f is conservative. So the question it asks you, verify that each of the force field is conservative. We've done this. Now find this potential f equals minus gradient of phi. So they're asking you a specific function, which is this. Now this is simply minus partial x of phi minus partial y of phi minus partial z of phi. Okay, and f, if you remember, was 1 minus z minus y. So if I equate these two, I'll get three different equations, which are partial x of phi is equal to minus 1, partial y of phi equals z, partial z of phi equals y. So somehow we need to find phi of x, y, z from these conditions. And there are enough conditions, as you'll see. First thing, let's number them, 1, 2, and 3. And the first thing that I'll do is take the integral with respect to dx of 1. This is what it will give me, partial x of phi dx. It will give me integral of minus 1 dx. Again, you have to take care of the constants. Since this is an integral with respect to dx, y and z are treated as constants. So in this case, I'll have integral of -1 is minus x plus a function of y and z, because y and z are treated as constants, right? Since partial x of f of yz is 0. So if I take partial x of this thing, I'll get -1 back. So you can see why this constant needs to be a function of y and z. Okay, let's do the same thing for the others. Integral dy of 2. If I do this quickly, I'll get yz plus some constant. Since this is an integral with respect to dy, I'll have a constant with x and z. An integral of dz of 3. So I'm taking the integral with respect to z of this one. I'll get yz plus another function which is with respect to x and y, because this is an integral with z. Okay, so we have 3 different equations now from these, and we can use them to find our constants. Our goal now is to find these constants. Well, they're functions with respect to y, x, y, and z, but the constant in the sense that we mentioned. Okay, so again, let's label these 1, 2, and 3. Now let's take the partial derivative with respect to y of 1, this one here. So in this case, I'll have partial y of minus x plus f of y and z. This will give me 0 plus f sub y of y and z. So f sub y means I'm taking df partial f over partial z. Okay, so this is partial y of phi by definition, and partial y of phi, as we said, was z. So I'll have f sub y of y and z equals z. Now, how do I remove this sub y? To remove this, I'll just integrate f sub y with respect to y. So I'll get integral dy z dy. Again, this is an integral with respect to y. So I'll have zy plus, and this is a function with respect to y and z. This is a function with respect to y and z. So the constant m, let's call it m, will be a function of z. Okay, so now we found f of y and z. This is from the fundamental theorem of calculus. Okay, so let's substitute. Phi equals from 1, I have this one, minus x plus f. Minus x plus f, which is minus x plus this thing, zy plus m of z. Now, how do I find this m of z? Well, we take, again, partial f by partial z of this thing. So in this case, I'll have 0. This will give me 0. This will give me y plus m prime of z. Now, partial phi partial z, from here, it's y. It's given to us. This is equal to y. So comparing the both sides of the equation, I can say that m prime of z is equal to 0. How do I get rid of this m prime? I simply integrate with respect to z. So this will give me m of z, which is integral of 0 dz. This time, since this is a function with respect to z, I'll get a pure constant. This is just a number. C can be e, pi, even I, anything. So now I have m, so I only need to substitute it inside here. So I'll have phi equals minus x plus yz plus c. This is our scalar that we are asked from the question. Okay, so this is how you find the potential. We call this the potential phi systematically. Of course, you don't need to do like all these three. You can do any two and solve for this. Okay, so let's do the next question, which is this one. So the question gives you a function f of x, y, z equal to 0. And they're giving you a point 3, 4, 25. And they're asking you to find the equations of the tangent plane and the normal line to the surface. Now, this is something that I skipped during the lectures, and because I didn't think it was, important in this course. But since one of you asked this question, I'm going to show you how to solve this. So the tangent plane. What is the equation of plane in general? You have in a 3D coordinate system, equation of a plane is ax plus by plus cz plus d equals 0. This is the equation of a plane. And where a, b, c, d, they're just some constant. Okay, so how do we make sense of this? In 1D, we had y equals mx plus b. This was the equation of a line, right, in the xy plane. Similarly, when you move into higher dimensions, you'll find this is the general equation. So this is how you convince yourself that this is indeed a plane. And also, if you take the gradient here, if I take the gradient on both sides, this and this, I'll find A, B, C. Actually, I'll just take the gradient on one side, equals 0. So this is actually a hint of how to find the equation of a tangent plane. So if I'm given a function f of x, y, z equal to any constant, not just 0, not just 0 as they gave you in the question, I claim that the tangent plane is simply this. A tangent plane at a given point at x naught, y naught, z naught is simply partial f, partial x, x minus x naught, plus partial f, partial y, x minus y naught, plus partial f, partial z, z minus z naught. The whole thing equals 0. Okay, this is the claim, and these are computed at x naught, y naught, z naught, all these derivatives. Okay, so let's do this. This is what I claim, and the justification comes from this. Since the tangent usually, if you have y equals mx plus b, the tangent is usually found by taking dy by dx. Similar to this, the argument is similar to this, so let's do this. First, let's find f is, what is f? X squared plus y squared minus z. If I take the gradient of f at the point they gave us, 3, 4, and 25, I'll have 2x, 2y minus z. If I substitute the coordinates, I'll have 6. Oh, it's not minus z, it's 1. So I have 6, 8, minus 1. So these are these numbers. So I'll have 6x minus 3 plus 8y minus 4 plus minus 1 actually. Minus 1, z minus 25. equals 0. This is our tangent plane. So this is our tangent plane. You can expand this and find a simpler form. I'll not do that here. So we found the first part of the question. Now the second part. Normal line to the surface. Again, this is something that I didn't teach you in the lectures, but since you've asked this question, I'm going to show you how to solve this. If this is our origin, you can imagine that a plane, if I take the normal to the plane, this is my normal vector n hat, normal to the plane. The distance, this distance d, is constant, right? Suppose I have a 3D coordinate, and if I have some plane like this, and if I construct a normal to the plane, the distance will actually be constant. This distance will be constant. So how do you find this distance usually? So the way we find this is simply x, y, z. This is r in the plane where x, y, and z are related to each other using the equation of the plane, where z is some function of x and y. So I'll have r dot n hat. This distance is simply r dot n hat equals d. This is the equation of plane. So if r is some x, y, z, then n, the direction of n, you can interpret these things, these numbers, to be the vector that is parallel to n hat. So I claim that the gradient of f is parallel to the normal. This is different. Notice that this is different from taking this. This is not the gradient. This is actually, a combination of the gradient with x minus x naught, y minus y naught, z minus z naught. So I claim that gradient of f itself will be parallel to n hat. This is from the equation of the plane. So I have 6. We found the gradient, 6, 8 minus 1. 6, 8 minus 1. N hat is parallel to 6, 8 minus 1. How do you find the equation of a line? The equation of a line is usually found like this. Since we're given a point 3, 4, 25, the equation of a line is given by this. So, x minus, you know what, I'll express it like this. In 1D, we had mx plus b, right? Y equals mx plus b, where m was the slope. Now, the slope in this case is this one. So you have, and x, since we're in 3D, we can no longer use x, we'll use t. So I'll write r of t. This is the equation of the normal. So I'll write capital N of t equals 6, 8 minus 1 t plus 3, 4, 25. This is the equation in parametric form, equation of a line in parametric form. So 3, 4, 25 comes from the point they gave you in the question, 3, 4, 25. And this is simply gradient of f at 3, 4, 25. This is, I think, quite simple. The simplest way to express the equation of line. And from this, you can actually find, if I say that this is x, y, and z, I can actually express this in terms of x, y, and z. So x is 6t plus 3, y is 8t plus 4, z is minus t plus 25. Okay, so that's the end of this question. Now let's see. I actually have quite a few more questions that I want to solve, but we don't really have a lot of time. Let's see how many we can do. Okay, so the next question is a differential equations question. this is related to relativity, and you're given an electron that is subject to a constant force F, and you're asked to find the velocity. This is not shown here, but this is a textbook question, and you're asked to find velocity as t tends to infinity and the position as t tends to infinity. Well, these are not vectors because they're in 1D, so you can remove the vector signs. Okay, so let's do this. They're giving you the expression itself. You just have to solve for v. So I'm given f equals d by dt of mv over square root of n minus v squared over c squared. And so you'll have m is a constant, so I can take that out. I can write f over m equals d by dt of v over square root of 1 minus v squared over c squared. Now, if I use the quotient rule, remember the one that we proved in one of our lectures before, in the fourth lecture, I believe, I can find this. So f over m equals dv by dt times square root of 1 minus v squared over c squared. I'm just using the quotient rule here, minus v times the derivative of this, so which is 1 over 2 square root of 1 minus v squared over c squared, times the derivative of this thing, which is simply minus 2v over c squared. I have an extra factor of c squared in here. So what will I get? I have to divide by this thing squared, the denominator squared. So I'll have 1 minus v squared over c squared. So, I missed a dv over dt here from the chain rule. So I'm just switching the sides here, dv by dt. And if I simplify this thing, which is not that hard, inside the bracket, I'll get 1 minus v squared over c squared. I'll take this as a common factor in the denominator, and I'll multiply with this thing. So together, I'll have a factor of 3/2. And if I multiply this with this, I'll have 1 minus v squared over c squared. And since I took dv by dt outside, in the inside, I'll have simply plus v squared over c squared. You can verify this. Well, let me show you how I got this. The minus and minus becomes plus. 2 gets cancelled, so I'll have only v squared over c squared left. Okay, so here v squared over c squared gets cancelled out. So I'm only left with dv by dt times 1 over 1 minus v squared over c squared raised to 3/2. Okay, so this whole thing equals f over m. So now I can express dv by dt as f over m times 1 minus v squared over c squared raised to 3/2. Now, if you classify this differential equation, this is of the separable kind. Since you have a function of v in here, and you have a function of t in here, which is 1. So this is separable. So let's solve this. So I have dv over 1 minus v squared over c squared raised to 3/2 equals f over m dt. And if I integrate both sides from 0 to t, and on this side I have 0 to v of t. Why 0? Because at t equals 0, the velocity, the electron is at rest. In the question, it says electron is at rest. Well, let's assume that the electron is at rest. So it will start at 0. Okay, so how do I solve this? I'll have to make a trigonometric substitution, which is V equals C sine theta. So dV will be C cosine theta d theta. So if I do this quickly, I'll have 1 over, let me take the C outside. So I'll have C cubed on top. You can verify this. And I'll have C squared cosine squared theta raised to 3/2 from the equation cosine squared plus sine squared equals 1 using this. And I'll have C sine theta d theta since this is dV. Okay, so, oh, it's C cosine theta, sorry. C cosine theta. So what will I have here? Integral of C cubed over C cubed cosine cubed theta, taking this 3/2 out, and I'll have C cosine theta d theta. So C cubed gets cancelled out, cosine theta gets cancelled out. I'll have integral of C sec squared theta d theta. And the antiderivative of sec squared is tan. So I'll have C tan theta d theta from theta at t equals 0 to theta at t equals t. Now, how do I find tan theta? I don't have tan theta in here. So this is simple. I'll just draw a right triangle in here. So I have theta in here. What is sine? Sine is the opposite side, this side, by the hypotenuse, right? And from the substitution, we have V equals C sine theta. So sine theta is V over C. So if this is V, this is C. So this side is V, and this side is C. So using Pythagoras theorem, this side must be C squared minus V squared. And if you notice, C is always the longest side in the triangle, of a right angle triangle. And C is the speed of light, the maximum speed. So it makes sense. So how do I find tan theta from here? Tan theta is this side by this side. So that is V over square root of C squared minus V squared. So I have F over mt, this is from this side of the equation, equals CV over square root of C squared minus V squared. Again, I can take C outside and I can cancel it with this one. So I'll have F over mt equals V over square root of 1 minus V squared over C squared. Now, if I solve for V, I'm going to skip some steps in here, but they're obvious steps. They're just algebra. I'll just give you the final form in here. That should be yeah, so the final form of V of t, if you solve for this, is F over m t over square root of 1 over t squared plus F over mc squared, the whole thing squared. This is our final form of Vt. You can do simplification here. I can take t squared out. Oh, actually, I've jumped the gun in here. This is the equation. I can take t squared out, so I'll have F over m t over t times 1 over t squared plus F over mc, the whole squared. Why did I do this? Because we're asked to find V as t tends to infinity. So if I substitute t the limit of t as infinity in here, I can cancel these out. I mean, whatever the mathematicians say, you cannot cancel infinity over infinity. You can justify this using L'Hopital's rule, but I'm not going to do it here. And 1 over infinity is 0. So I'll have f over m over f over mc if I take this thing, the square root of this thing. So f over m will get cancelled out. I'll only have c left. This is what we're supposed to prove, that vt tends to infinity equals c. So what this is telling us is that if you give an electron a constant force, f, it will eventually reach the speed of light. But this is not really physical. As you have taken in modern physics, nothing with mass not equal to 0 can ever reach the speed of light, because the energy required will be infinity, which is impossible. Okay, so there's a second part to this question, which is asking us what the distance x as t tends to infinity is. Again, we can do this using an integral. I'm not going to do this because x is simply v dt, and it's a simple substitution here. See, I can just take 1 plus this whole thing as u, and du will be 2 times this. So I can already do an easy substitution in here. I'm not going to do this. Okay, so let's move on. We've solved all the problems that you've sent. Are there any questions on these so far? No questions? Okay, so let's move on. Now I'm going to give you a question on differential equations, since we haven't really done a lecture on this. So this is going to be about a circuit, an electric circuit, and you have to find expressions of current or charge depending on the situation. So I have a circuit like this. I have the capacitance C, and a resistance R, and an inductor L connected to a voltage source that is changing with time. How do I write the equation of this circuit? I use the Kirchhoff's rule, of course. So to use the Kirchhoff's rule, I need to find the voltage of each component on its own. So from 102 or physics 241, you will have learned that C equals Q over V. So V equals Q over C. And from Ohm's law, I have V equals IR. And although you haven't taken it, this is VR, this is VC. VL will be L di by dt. And using Kirchhoff's rule, I can take this loop and I'll have VR plus VL plus VC equals V of t. These are the dissipative components in your circuit. This is the source, the input. Okay, so usually you write let's write it in order. You have IR plus L di by dt plus Q over V. Oh, it's Q over C. Equals VT. VT can be anything. It's usually sinusoidal. Usually it's like this. But it can also be 0, depending on the question. And so, as you can see, I have 2 different variables here. I have I of t and Q of t. So what do I do to convert Q to I? I can take the time derivative of both sides. So I'll have di by dt, or di by dt, plus L d squared I by dt squared plus dq by dt, which if you remember is I. So I can just write I over C equals dv by dt, which is usually not going to be difficult to do. And it can also be 0, in which case it will be simpler actually. So I'll to write this in the standard form in which the coefficient of d squared, the second order term is 1, I'll have to divide everywhere by L. So I'll have plus 1 over, plus 1 over L over R. Oh, so I was dividing by L. So I'll have R over L di by dt plus I over RC equals dv by dt. This is the equation of the circuit itself. And as you can see, this is a second order linear differential equations. Linear equation because the coefficients are constant. R, L don't change with time. And usually you solve this using operator methods. So I'll define an operator capital D as d over d derivative with respect to time. So d squared will be d squared over dt squared. And for convenience, I'm going to write this as 2 gamma and 1 over RC. 1 over RC. I'll define it as omega naught squared. There are actually physical meanings for these values, and you learn about them in classical mechanics if you take it next semester. So I'll have d squared minus 2 gamma d plus omega naught squared, the whole thing acting on I, equals v of t, dv by dt. Let's suppose that dv by dt is 0, so it's the homogeneous case. The solution in this case is I equals e raised to a e raised to r1t plus b e raised to r2t, where r1 and r2, these are the zeros of this polynomial. And if you notice, like, the use of operators is not very strange, because we've dealt with operators like the gradient, the divergence, and curl. So, and the Laplacian as well. So it's not that weird to consider this thing to be an operator. And the reason this works out is because this thing is actually, in addition to being an operator, there's also a polynomial. You can treat this as a polynomial, and that's why you have this property. Okay, so in this case, what will my solutions be? R1 and R2. I'll find them using the quadratic formula. So R will be minus 2 gamma is plus 2 gamma, plus or minus square root of 4 gamma squared. This is 2 gamma the whole squared minus 4 omega naught squared. The whole thing divided by 2. So this is going to give me gamma plus or minus, if I take this 4 outside, it will become 2 here, and it will cancel out with this 2. So I'll have, inside here, I'll have gamma squared minus omega naught squared. Usually you have omega naught greater than gamma because of physical reasons. Omega is related to the natural frequency. Suppose I have a pendulum, the frequency with which this oscillates is usually omega naught. And gamma is the damping coefficient. So suppose I have this inside a bucket of oil, for instance. The oil, will oppose the motion of this ball. And the proportionality constant, so the force, the drag force we say, is proportional to the velocity of the object. So the constant is actually F drag is 2 gamma V. Okay, so this is how you solve. So having found R1 and R2, you can simply write I of t equals, this is the homogeneous part of the differential equation solution. So I have e raised to gamma t is constant, and I have e raised to, for convenience, I'm going to denote this by omega, e raised to omega t plus b e raised to minus omega t. Okay, so one last thing, the simple harmonic motion. And then we end this lecture, which really went over time. So if you have a solution of a differential equation, usually the simple harmonic motion has a differential equation of the form d squared plus omega naught squared of some quantity theta equals 0. So this is the general form of simple harmonic motion. So in any physical physical situation, physical problem, you may have a bucket filled with water, and you may have a block that is floating on it, and you displace it slightly, like you push it in, and this thing will oscillate with some frequency. If you write the equation of this, you'll find that it's of this form. And similarly, for a pendulum with small angle oscillations, where theta is small, you will have an equation of this form. So in these cases, theta usually has the form a cos omega t plus b sine omega t. Or you can express this as a cos omega t plus some phase factor phi. And again, a note in here about differential equations. For an nth order differential equation, you will have n arbitrary constants. I'm reminding this to you because we haven't really done a lecture on differential equations. So in this case, I have a and b, and in the second case, I have a and phi. So this is what simple harmonic motion is all about. If you have a differential equation of this form, where d is, d over dt or d over dx, depending on your problem, and if you have a solution of this form, you have simple harmonic oscillations. And with that, I've finished. Hopefully, you've benefited from the review. If you have any questions, you can send me a message, and I'll be happy to answer your questions. And before I wrap things up, I want to know if any of you have any questions. Okay, non-homogeneous systems. Actually, there's a question about non-homogeneous systems and using operator methods. In fact, we can actually use operator methods for non-homogeneous equations. I'll just take 2 or 3 more minutes for this. So I'll not be able to, I don't have the time to prove this. So let's use the example that we had. This example, the circuit one, which is this one. Okay, suppose dv by dt, this quantity, was not 0, and say if it was some function f of t. The cases, like there are only special cases in which you can use operator methods for non-homogeneous differential equations. And usually that's when f of t is of the form some constant a times e raised to I say omega t, right? This is the case. Like this can also be a cosine omega t, like it can be purely real, or a sine omega t. So this is what we call a sinusoidal input. The output will be sinusoidal. Okay, so the way we deal with this is that I will have a homogeneous part, that is the solution when this thing is 0, and you'll have a complementary or a particular part that is going to be related to the input itself. Okay, so the homogeneous part, we've seen the solution. How do we find this one? My claim is that if I consider this to be P of D, so the equation will be P of D. P of D is basically a function, a polynomial function. P of D of I equals A e raised to I omega t. If I have a differential equation of this form, the solution will be, I claim, P of omega, A e raised to, no, it's not going to be A itself, it's going to be some other constant, e raised to I omega t over P of omega. So you substitute omega everywhere you see a D in here. So I'll have omega squared minus 2 gamma omega plus omega naught squared. E raised to I this thing. Okay, so no, it's not that actually. It's going to be divided by this thing. And you'll have A e raised to I omega t over omega squared minus 2 gamma omega plus omega naught squared. Okay, so this will be a solution, and from this, using properties of complex numbers, you can have an amplitude part and a phase part, which you can discuss later if you want. But yes, we can deal with differential equations that are not homogeneous using operators, but it's only limited to special cases. If you want to, go deeper, you have something called the Laplace transform, which can be used, for any given functions. Like, not for any given functions. If you have nice functions which are easy to integrate. Okay, I hope this gave you some insights about non-homogeneous differential equations. And with this, I conclude our lecture. Thank you very much for attending, and Ramadan Mubarak. Okay.